All right, team, welcome to today's explainer. Go ahead and grab a coffee, because today we're putting on our tech lead hats. We're setting a really focused, collaborative tone for this briefing because, well, we're tackling one of the absolute most stubborn bottlenecks in our entire software development lifecycle. Yep, we're talking about upgrading our testing pipelines. We're going to look closely at how integrating generative AI is completely transforming the way we validate our code. We're talking about moving away from those rigid manual test creation workflows and stepping into the world of intelligent, automated quality assurance. It's going to be a fun one.
Okay, let's dive straight into this with a pretty brutal question to kick us off. Are unit tests actually catching bugs, or are they just executing code to hit some arbitrary coverage metric? We really need to talk about this. We so often rely on line or branch coverage just to keep management happy, right? But standard code coverage, it really only tells you if a line was touched. It absolutely doesn't tell you if your tests would actually fail if someone accidentally broke the logic. We've got to challenge this whole assumption that standard code coverage automatically equals quality.
Let's ground this in reality for a second. Look, we have all experienced those absolutely soul-crushing late nights, hunting down intermittent bugs, or worse, production incidents that somehow slipped right past our supposedly perfectly green test suite. Traditional testing eats up anywhere from 15 to 80% of a project's budget, and yet these massive blind spots just remained. So today, we're looking at AI automation, and not just as some neat, shiny new toy, but as our new strategic advantage to ensure our test suites actually prove our code works. So how do we solve this blind spot? We use mutation testing. Think of it like a stress test. Actually, scratch that. It's more like injecting a digital virus directly into your codebase. We programmatically introduce minor, highly realistic faults. We call these mutants. So imagine flipping a greater than sign to a less than sign. Then we run your existing unit tests. If your tests are strong, acting like a healthy immune system, they'll detect that fault and fail. We call that killing the mutant. But if the tests pass anyway, well, that mutant survives, and it just exposed a very dangerous gap in your assertions. So here is our sprint plan for today's briefing. We're going to cover the AI testing shift, do a quick model face-off, map out some tactical prompting, look at how AI fits into the CI pipeline, address the very real trade-offs, and wrap up with a pragmatic conclusion. Let's get to work. Section 1. The AI testing shift, moving beyond traditional rules. For literally decades, mutation testing has relied on incredibly rigid syntax rules. But by stepping away from those rules, the results we're seeing are massive. Studies are showing that context-aware, LLM-generated mutants achieve a 1.75 times improvement in real bug detection compared to your traditional syntactic operators. This is huge. AI models don't just blindly flip operators anymore. They generate naturalistic mutants that actually mimic real-world, everyday developer mistakes. Now, what's really interesting about this data is the sheer scale of the performance gap here. When you look at fault detection rates, traditional tools like PET sit way down at 40.1%, and Major is at 66.9%. But then you look at the AI-driven approach, specifically LLMute using the DeepSeek-V3 671 billion parameter model. It achieves an absolutely astounding 91.1% detection rate. To put that into perspective, that is a staggering 32.99 percentage point absolute gain in finding actual, real-world bugs. Moving on to Section 2, Model Face-Off, General versus Specialized Models. Now, AI isn't some monolith, So let's break down the landscape of the models we actually have available for this. On one hand, we've got your general-purpose models. Think GPT-4o and DeepSeek-V3, which boasts massive parameter sets, up to 671 billion. On the other hand, we have code-specialized models, like CodeLlama or DeepSeek Coder v2. These are significantly smaller, usually ranging from 13 to 236 billion parameters. But they're explicitly fine-tuned on vast repositories of source code. And there are definite architectural trade-offs here. General models are fantastic at complex logic. They're great at understanding the deep, natural language reasoning behind your code. Like, they might infer that if you have a variable named right block, there's probably a left block somewhere too. However, specialized models are often much more efficient at generating syntactically valid code that adheres strictly to programming paradigms. They give you far fewer fundamental syntax errors, and honestly, they do it at a much lower computational cost. All right, Section 3, Tactical Prompting, Structuring the AI Agent. Now for the tactical how-to phase. This right here is the anatomical structure of the perfect AI prompt for generating mutants.
If you just dump raw code into an LLM, honestly, you're just going to get noise back. Step 1 is the instruction. You have to define the exact role. Step 2 is the context. Supply the specifically targeted method code. Step 3 is absolutely crucial. Few-shot examples. You have to show the AI exactly what a real bug looks like. And finally, step 4 is your output indicator, strictly demanding a structured format, like JSON, so our automated CI pipelines can actually parse the response. So the crucial point I want you to take away here is context management. Studies highlight that providing exactly 6 few-shot examples sourced from real-world bugs like those in the QuicksBugs dataset drastically reduces the chance of the AI generating syntactically invalid code. Also, please do not feed an entire file to the model. That just completely overwhelms the context window. You've got to focus purely on targeted method snippets. Which brings us to section 4, AI in the CI pipeline, deployment architecture. Let's look at how we actually bake this into our daily DevOps workflow without breaking everything. We deploy this in phases. At minute 0, the pre-commit phase, we're just running lightweight checks locally on the specific files you changed. At hour 1, the pull request level, we run a targeted subset of AI mutants prioritized by risk, just to give you really fast feedback. And then finally, at hour 24, we do the nightly run. This is where we unleash the full, comprehensive AI mutation suite across the entire default branch. We literally stress test the entire system while we sleep. And this brilliantly illustrates our core architectural philosophy here. We are building a Gen AI microservice that acts as a highly intelligent assistant. It is absolutely not a fully autonomous autopilot. We maintain a very strict human-in-the-loop workflow. The AI can suggest tests for surviving mutants or triage equivalent mutants, but a human engineer must review and validate those suggestions before they ever merge into our codebase.
Section 5. Trade-offs and realities. The cost of intelligence.
Now, to be credible engineers, we have to candidly look at the raw cost of all this intelligence. AI gives us incredibly high diversity. Research shows LLMs can introduce 49 entirely new abstract syntax tree node types. They make complex, context-aware changes that uncover some seriously deep edge cases. But AI models still struggle with a 32.73% drop in compilability. That's a real headache. Meanwhile, traditional tools like Major or Pit, they are blazingly fast. Supreme execution efficiency, boasting a 97.6% compilability rate and absolutely 0% duplicate mutant noise. So the reality? AI is definitely smarter, but traditional tools are currently much more reliable.
Finally, Section 6, the pragmatic conclusion. Bringing this sprint plan to a close, it's clear that combining the precision of mutation testing with the generative power of LLMs gives us a massive, massive leverage point. But that's only true if we manage the noise. We have to use AI to generate the mutants and draft the tests, for sure, but we still have to rely on our own engineering intuition to review them. As the research perfectly summarizes, organizations that treat Gen AI as an assistant, not an autopilot, and tie mutation testing to risk will win. So I'm going to leave you with this final provocative thought. Are your pipelines actually ready to survive the ultimate AI-generated stress test? Take these strategies back to your teams, upgrade your prompts, and let's start catching those nasty bugs long before they hit production. If you found this explainer valuable today, make sure to like, share, and subscribe for more deep dive engineering playbooks. See you in the next sprint.